Hi everybody, we're going to start our series of videos for chapter 12 with this video. This is probably the biggest chapter we'll have since chapter 8. Remember how big chapter 8 was? We had to learn all the vocabulary and procedures for running a hypothesis test for the first time. If we were still running this class live, what we would find is that I'd be going for the regular 2-hour session, and then we would still have about 15 more minutes left over that we would have to do the next day on the quiz. So all that by way of saying that this is another big chapter. But the good news here is that we are essentially doing the same old thing we've always been doing. We are essentially going through the same 4 steps. But we are now done with all of our t-tests. So we did our single sample t-test, independent measures t-test, repeated measures t-test. So now we're turning the page into what we could call F tests, I suppose, because the letter we're going to use is a capital letter F. But this chapter and the next chapter are both doing what we call ANOVA. And ANOVA is an acronym. It stands for AN, Analysis of VA Variance. So ANOVA is just a shortcut way of saying analysis of variance. The key here is that in chapters 10 and 11, our independent measures t-test and our repeated measures t-test, we had 2 sets of data. For independent measures, we had a set of data taken from one sample and a second set of data taken from a completely different sample, right? Independent, 2 different samples representing 2 different populations. And then in repeated measures, we had the same sample measured twice. Measure them, give them a treatment, measure them again and see if they're changed. The basic reason for using ANOVAs is to test for 3 or more treatment conditions. Now, technically your book says 2 or more, and that is true, but there are only special circumstances why you would do an ANOVA with only 2 treatment groups. So what we're going to say is 3 or more, even though technically you can do it with 2. So now, instead of saying what is like somebody, let's say we're doing independent measures, and we're going to get a sample that is not receiving a medication and a different sample that is receiving a medication, and we can compare those 2 groups. But what if we want to compare 2 different dosage levels? So people without the medicine, our control group, people taking, let's say, 10 milligrams of some medication, and then another set of data for people taking, we'll say double that, 20 milligrams, so 0, 10, or 20 milligram dosage of a pill. Well, that would be 3 different treatment conditions. And we could do the same thing. We could get different samples for every group in independent measures, or we could run the same sample through all 3 conditions, our repeated measures. We can still go independent measures or repeated measures, but the key here is we're doing 3 or more different treatment conditions. So that is the key for us here. So analysis of variance. Remember, the word variance just means differences. To analyze something is to break it down into smaller pieces. That's literally what it means. We tend to use that word in a lot of ways informally, but the literal direct meaning of that word is we're going to take an idea and break it into smaller pieces. So we are going to look at the differences in our data, the differences in the scores we've gathered, and break that down into smaller units for comparison. At the end of the day, we're still trying to answer the same question. Are these sets of scores different from each other or not? Do they have statistical significance? Only now we've got lots of different groups that we can compare instead of just 2. So ANOVAs can either be independent measures or repeated measures. This chapter is going to be specifically for independent measures. Independent measures, so separate samples representing separate populations. So if I did that medication study, 0 milligrams, 10 milligrams, 20 milligrams, if I had different people in each sample, that would be independent measures. If I wanted to compare college freshmen versus college sophomores versus college juniors versus college seniors. That's 4 different treatment conditions, and I would probably want to do that as an independent measures. Get a sample of freshmen today, get a sample of sophomores tomorrow, get a sample of juniors the next day, get a sample of seniors. Different samples representing different populations. We're typically only going to do with three treatment conditions at a time. Now, we're going to see in a couple of ways in this chapter old ideas we already know, existing vocabulary, but they use new terms for our old ideas in ANOVAs. Kind of a drag, I know, but that's the way it goes. So one of the things that we need to also address is the term factors. A factor is a new vocabulary word for us in this course, but it's a new word for an old idea. When you see the word factor, it means independent variable or treatment. So that's just the language we use in ANOVAs. So for whatever reason, they don't use the same terms. So we could have 1 factor or 2 factors or 3 factors. It's how many treatments are there. So imagine that I wanted to know in this medication study, 0 milligrams versus 10 milligrams versus 20 milligrams. That's 1 factor. It's all 1 treatment. It's medicine. There are 3 levels of that factor. The levels of a factor is referring to the values, or the other word you may know for this is attributes, the values that the factor can take in your study. So the factor is medicine, and there's 3 versions of it. None, 0 milligrams, 10 milligrams, 20 milligrams. There are 3 levels, 3 versions of medication, none, some, or more, 0, 10, or 20 milligrams. So that factor has 3 levels. We would see very often in published research ANOVAs that have more than 1 factor. So I also might very much want to know about the differences between males and females with this medication. We know that male biology and female biology often responds differently to medication. So another factor would be biological sex, of which there would be 2 levels or 2 versions, females and males. So in one experiment, I could have both of those factors going on at the same time. I could ask, how do the men on 0 milligrams perform compared to women on 0 milligrams, compared to men on 10 milligrams, compared to women on 10 milligrams, compared to men on 20 milligrams, compared to women on 20 milligrams. Notice that that would take 6 different samples for independent measures. I need a group of men not taking it, taking 10, taking 20, a group of women not taking it, taking 10, taking 20. So we can have multiple factors. We can even have 3 or 4 factors going on at a time. So we can get a sense that that's going to be very, very complex. But we're going to make it as simple as possible. In this chapter, it's our beginning one. It's our first ANOVA. So we are only doing independent measures, ANOVAs, right now. And we are only doing single factor. So this is the easiest, simplest version of an ANOVA that we can start with. So we are doing single factor, only 1 treatment, independent measures, different samples representing different populations, analysis of variance. So this is our starter one. We will, in the next chapter, look at repeated measures and talk some about if we had 2 factors or more. But even doing 2 factors isn't even part of this chapter. It's not even in there. So we'll get to that another day. That's what we're working on here. Again, single factor, independent measures, ANOVA. Remember with the different types of t-tests, and I said the first thing you got to know is which t-test to run? Same thing is going to be true with ANOVAs when you're taking in your last exam here. I'm going to give you a problem, and you're going to have to know which ANOVA is it. Well, it's either going to be independent measures ANOVA or repeated measures ANOVA. So it's a little bit simpler. It's more of a 50-50 coin toss. And we are only ever going to directly work on problems with single factor. We're going to talk in the next chapter about vocabulary for 2 factors or more, but we're never going to calculate that stuff. It's way too much calculation to do by hand with a calculator. We would want to use computer software by then for sure. As we're going to see, this one is already a fair amount of calculations. It's 9 calculations we'll be doing to do this one type of problem. But the good news is they're all calculations we mostly already know, just twists on things. but it's analysis of variance. We know from chapter 4 the formula for variance is sums of squares divided by degrees of freedom. So we're going to have lots of sums of squares values, lots of degrees of freedom values. It gets us lots of variance values that we'll be comparing in our test. So that's what we're starting with here. That's the type of test we're doing. Now, and I'm going to put an abbreviation up here, single factor. Just to remind ourselves fully that that's what we're doing, a single factor independent measures analysis of variance. Some of you might think to yourselves, well, I'd rather not learn all this. I'm sure that's most of you anyway. But with the rationale of, I already know how to do independent measures t-tests. I already know how to compare two groups. So let's think about it. Let's say I have one sample that has a mean of 20 points on whatever we're measuring. And then I have a second sample that has a mean of, we're going to say, 30 points. If we just had two samples, two sets of data, I could fairly ask the question, what is the mean difference between these two groups? What's the difference between the means? 20 points, 30 points, what's the difference between them? 10 points. The mean difference is 10 points. Fair enough. But when I add a third group in here, if I try to ask the exact same question, what is the mean difference, we run into a bit of a problem. Because there's three different differences to talk about here. There's 10 points between group 1 and 2, 15 points between 1 and 3, and only 5 points between 2 and 3. So it's difficult to just subtract an answer like we could have done when there was just the two groups, 30 minus 20, 10-point mean difference. But with three groups, if I say, what's the mean difference? Well, there's not one answer to that. We don't have a way of asking or answering the question, what's the difference between three groups? But we do have a tool from way back in chapter 4 that can take a whole bunch of numbers and calculate on the whole how different from each other are they. Variance. Remember, variance, when we calculated variance, we just took a whole bunch of raw scores and made one calculation to say, on the whole, across all that scores, how different from each other are they? Well, we're going to basically do the same thing here. We're going to calculate variance to look at the differences across all the numbers at once, and then break that variance into pieces. So, again, someone might well say, well, Paul, if this is my setup, I could run three different independent measures t-tests. I could run a t-test between groups 1 and 2, see if they're significantly different from each other or not. I could run another test from groups 2 and 3, see if these two groups are different from each other or not. And then lastly, I could run a third t-test between group 1 and 3 and ask if those two groups are different statistically from each other or not. You could do that. It would be a mistake, but you could conceivably do that. It actually works out to be the exact same amount of math. So it's not about more math or less math. Think about your t-test. You always had three things to get, right? You had to get your variance, some measure of variance, some measure of error, and then your t-statistic. Well, to do an ANOVA, it would be 9 calculations anyway. So if we did a bunch of t-tests, 3 calculations plus 3 calculations plus 3 calculations, we'd have 9 calculations. It's not about more math or less math. It's different math, but it's not that. Let's stop and consider if we did this first t-test at an alpha level of 0.05, and the next one we ran an alpha level of 0.05, and the last one we ran an alpha level of 0.05. If we did this as 3 t-tests with an alpha level of 0.05, each test we would run would have a 5% chance of making, remember, a type 1 error. Your alpha level is your odds of making a type 1 error. So what does that mean? Across this single experiment, there are 3 tests. This is all one big experiment, but there are 3 comparisons. Test means a comparison. So this comparison, we'd have a 5% chance of making a type 1 error. And then this comparison, we have another 5% chance of making a type 1 error. And then the last comparison, we have another 5% chance of making a type 1 error. It doesn't literally work out to be 15% for some weird math reasons, but we don't have to worry about it. Let's just call it 15%. That means across the 3 tests, my single experiment has a 15% chance of a type 1 error. That's an alpha level of 0.15. This is why we don't want to do a bunch of t-tests. Because t-tests are going to inflate the risk of making a type 1 error across the entire experiment. Each test is only a 5%. Each comparison is only 5%, but it's all one big experiment. So we've got 5, 10, 15% chance, again, not exactly, but close enough, 15% chance of making a type 1 error. We know that's unacceptable. This problem only exists because we've got the 3 groups. So we have some ideas to think about here. There's what we call our test-wise alpha level. And then we have the experiment-wise. Alpha level. So when we are in our step 2, choosing an alpha level, what we're doing is we're picking an alpha level for the entire study at once. That is the experiment-wise alpha level. So test-wise alpha level tells you your alpha level for any one comparison. So what I just erased, remember, had 3 comparisons. But when we want to set our alpha level, we want to do it for the entire experiment, the entire study at once. So when we pick an experiment-wise alpha level in step 2 of, say, 0.05, that means the entire experiment, all the comparisons combined, only have a 5% chance of making a type 1 error. That means every little comparison within that, every little test within that experiment, the alpha level will actually be much smaller than 0.05 because they all have to add up to 0.05. So again, your test-wise alpha level is the alpha level for a one specific comparison. Well, if we think about our independent measures t-tests and repeated measure t-tests, we're only ever making one comparison. There were 2 sets of data and there was only one comparison to make. So the comparison and study levels were the same. There's only one comparison and there's only one study. So that's why we didn't have to talk about it till now. But now if we've got 3 or more groups, there are multiple comparisons, but still only one study. So the reason we don't want to run a bunch of t-tests is because we don't want to inflate the risk of making a type 1 error in the experiment. If we run a bunch of t-tests, we inflate the experiment-wise alpha level and therefore inflate our odds of making a type 1 error. So that's why we don't want to do this as a whole bunch of t-tests. We want to just do this as one big study analysis. So that gets us started into this chapter. Next up, in the next part, we'll look at sort of the overview, the logic of what we're doing, what we're breaking into pieces here. So we'll see you in the next part.